Okay. Wait 1 second. Okay. Uh, let's see. You still going on here? So you're not getting any echo, right? I'm getting it there, but you're not getting it there. So that should be fine. Okay. I am still actually, yeah, no, there is actually. Hello? Okay, no, I need to read this. There is a way. Yeah, computer audio has to be left. I'm trying to, hello? Oh yeah, I can hear this still. Um, I'm trying to remove the computer audio from here. Okay. Oh well, let's see what happens. Oh, God. Yeah, so I'm not too sure of the recording quality. What I'm going to do is I'm again going to record it on this too. And then I also sent you the PDF slides. Okay. So today, sheesh, this is very annoying. I'm sorry. Give me a second. I just try to figure out what I can do with this. Ah, yeah, there used to be a way in which you can remove the. Oh well, this is not good. Okay, I have to just try this. It's annoying for me, but at least it's not annoying for you. So I'll probably try to stand um, here. So we're going to talk today about the two chapters that you read. I'm not going to check whether you read for this time. I hope you did, but next time onwards, in general, you would follow it better if you have actually read the chapter. And if you have any questions, you can bring them up. I actually asked people to um, put the yeah put the questions on the piazza, but I don't think anybody did. As far as I can tell, I didn't see anything. So, are they before we get started? Are there any questions? I mean, I'm going to kind of walk you through my own version of these two chapters for today, at any rate. But are there any questions that you have that will set me? That'll give me some idea of what you understood and what you didn't understand. Yes.
They talked about how I talked about like how so many managers like discussing expected cost rather than like the cost of the space scenario. But I was wondering how is that like practically used when it comes to
Yeah, so we will talk about partially observable MDPs, etc. later on. It becomes, again, that chapter is basically talking about farther down the road, in the beginning. But in general, like there are a whole bunch of issues in terms of partial observable MDPs. As I said last class, they will be searching in the space of what I call belief states. So, and even if you have a discrete state space, that means you have like only n states, you will wind up having infinite number of belief states because a belief state is just um, a probability distribution over the states. And there are many, many probability distributions over the, let's say K states. And so POMDPs really can be thought of as MDPs on continuous state spaces. Okay. And that's basically, but I mean, when we get there, we'll talk more about that. And the other aspect of it is in terms of expected versus worst case. In general, when you have stochastic, dynamics, then you can be either maximizing the expected performance. But one of the other things that people are interested in is minimizing the worst case performance, right? For example, if you're trying to fly a plane, part of the design of the plane has to take into account minimizing the plane crashing as against maximizing the speed with which the plane will just travel. Do you understand what I'm saying? So those become also, so there are different ways of looking at goodness of policies. And in talking about robust policies, you typically tend to talk about something more than just expected cost of the policy, because there can be expected cost, but there's a huge variance. And if one of the bad things happens, then you are in big trouble. In fact, one weird situation that's kind of close to home is, honestly, the expected best policy for autonomous driving has probably been found long back. But if you have even one fatality involving humans, it basically winds up being a much, much higher cost for the company, because the company will have to actually close down its autonomous vehicle division. And so as I was saying earlier, part of what you could say Waymo was doing for the last several years was just trying to make sure that the edge cases are taken into account, which is an extremely costly process on their part. But then if you don't do that, and if you just say on the expected level, it seems to be a pretty good policy, there would be accidents and people get mad. So that's connected to robustness. And this actually also, interestingly enough, connected to the use of AI technology these days in any decision-making task. Okay. The thing is that you could always say that AI systems are better than random humans on something. Let's say on figuring out fraudulent credit card transactions, or figuring out how much of a culpability somebody has. Basically look at the face of the defendant and say guilty, not guilty. Do you see what I'm saying? Actually, AI systems might well have a higher performance than most random humans, for example. Okay, so on the expected cost, they might actually be doing well, but then the downside can be quite high. And one weird thing is, even though you get to drive on the roads, right, and most of the time you drive well, the one time you are looking at the cell phone and you hit the pole, and worse yet, a kid on the road, they don't give like the benefit of doubt, saying, he's been driving so well for so many years, one little kid, what happens? No, you will actually spend time in the jail, most of you, unless you have like rich father and mother. Okay, you will spend time in the jail. So the question is, what is that for autonomous AI systems. So in general, when people say people also make mistakes, so AI systems are good enough given the fallibility of humans, you have to ask yourself, how do I put ChatGPT in jail? What does it actually mean to deter bad behavior, whether it is intended or not? Okay, and if that is not there, then you won't actually look for robust behavior. You'll only design for expected better behavior. Okay, so that's kind of a longer connection to what are you actually optimizing for. Okay, this is really bothersome. Okay, let's see. Okay, so I think it's just all my students are missing today, I guess. Let me try to get out of this once and then just try to rejoin this again, because this is not helping for me.
Progress.
Yeah, this is the problem. There should be a way in which does anybody remember how we get out of the computer audio on the Zoom? Oh, disconnect audio. Good. Hello? Yay! Okay, good. I'm so damn good. Okay, thank you. Yeah, next time remember, see the join audio has to be disconnected. Otherwise, I'm hearing myself and I'm getting sick of it. I don't know how you stand it, but anyway. Okay. And then I need to restart the Zoom sharing. Share content, screen, and then. Yeah, this is the new and improved easy way to teach classes, which involves 18,000 extra steps. Even though you are standing in front of me and we can't talk to each other, right? That's the problem. Yeah. Okay. Great. So that's about expected cost thing. We see. Yeah. So I'm just going to walk through some of these things in terms of getting us to think about the simplest form of deterministic planning. Okay, from fully observable deterministic planning scenarios. We'll start from there and we'll go into stochastic, et cetera, et cetera. And one of the other things we'll find is the way you model the planning problem, you can do it in what are called atomic states, where you essentially think states are indivisible black boxes, S1, S2, et cetera, S1000, and the actions essentially transform states to states. Okay, and in particular, actually, a deterministic action, when applied to a state, takes you to at most one state. A stochastic action, when applied to a state, will take you to some set of actions non-deterministically. And the difference between non-determinism and stochasticity is the non-deterministic action really, you can't tell which state it's going to take. It's say if you do this action, you will get either S1 or S2 or S3. You can't tell with what probabilities S1, S2, S3 is happen. If you know the probabilities, that extra knowledge. Do you see what I'm saying? You know, basically the S1, S2, S3 non-determinism means any probability distribution. You just don't even know the probability distribution. Okay. So anyway, that's basically atomic thing. So we talked about this operator planning big picture. We talked about domain independent and domain dependent planning last time, right? And then we should look at these are the different types of environments. You should know that ultimately all this agent is trying to do is what action should I do next? And the problem itself depends on, first of all, what are its goals? Okay, what are the goals it's trying to achieve? And the interesting thing is the goals can be achieve the following, get to the following state, or achieve the following, more abstract description, which means many different states might actually satisfy that. Okay, and even more interestingly, you can also have a description of the goal which says achieve a state while making sure that the following properties hold while you are reaching that state. So for example, a driver goes from here to Sky Harbor, let's say, that's the goal. But you have bad and good drivers. The driver who makes you kind of hang on to your life while driving to, Sky Harbor because they're running red lights and, killing a couple of people here and there. They're not good drivers, even though they achieved the goal. Do you see what I'm saying? So you could actually have legitimately goals that actually give path constraints. Not just the achievement, what you reach, but also what sort of things should you do while you are, on the business, on the process to reach. Okay, and sometimes, interestingly, the goals may not even actually have a specific state that you have to reach. It could be essentially live well, do the least amount of violence, things of that kind. So those are goals too. And you might well say, given two very different policies, you can say this one seems to be worse than this in terms of satisfying this abstract goal. But in the beginning, we will think the simplest case of goals is goal of achievement. So we will say, I want to reach a particular state. That's where we'll start. Okay, I'm in a particular state. I want to reach another particular state of the world. Okay, the kind of actions I have can be deterministic or stochastic. Deterministic essentially means that if you do the action, it will at most take you to one more state. I mean, if it doesn't work, then you just remain in the same state. That's the way to think about it. Okay, stochastic, as I already mentioned to you, stochastic is basically it takes you to a distribution of states. Observable versus partially observable is, does the agent know which state it actually is in? Okay, and interestingly, this can be a question like across the board. It may not, the special cases of not knowing where you are include, you don't know where you are starting from. You don't know where you are in the middle of the plan. You don't know where you are at the end of the plan either. Do you understand what I'm saying? So one of the most famous examples that, how many of you know bomb in the toilet problem? This is the kind of big bucks you pay to learn about these kinds of things in this class, okay? So bomb in the toilet problem is like the most important problem you should remember to understand how you may be able to achieve a goal even if you don't know which state you are in. Ask yourself the following question. You have friends who might be visually challenged. Are they able to achieve goals? Right? Not all goals, maybe, but they are able to achieve a whole bunch of goals. Okay, and so the interesting question in the bomb in the toilet problem is, okay, I don't know why this keeps going backward. Bomb in the toilet problem is that you have, you go into a toilet, there is a package next to the toilet, okay? And that package may or may not contain a bomb. May or may not contain a bomb. So you don't know which state you are in. Okay, so that package may contain a bomb or it may not contain a bomb. That's the disjunction of states you are in. Okay, and the only thing is that if you try to, one idea is to test, open the package to see what is there. But as we all know, if you try to open a package with a bomb goes off. So you shouldn't touch the damn thing to open it, etc., etc. However, thankfully, there is a beautiful way you can diffuse any bomb. You flush it down the toilet. It is somebody else's problem. Right? You flush it down the toilet and that's it. Okay. So the question then in the bomb in the toilet problem is, can you solve it? Can you, the goal is to not die. Okay. You notice that even though you have eyes, you are effectively blind in this problem. Do you understand what I'm saying? You see the package, but you don't see what is inside the package. Unless you have some kind of those Superman X-ray eyes or something. Okay. So you don't see what is inside the package. And the question is, are you going to just basically be able to survive? And how many of you think you can survive based on what I just said? This guy won't survive? My God, I don't know what's going to be. How do you survive this problem? I mean, how do you ensure that the bomb doesn't go off? Flush the damn thing. That's what we do. We don't care. It's like, right? Just flush the package. If it has a bomb, it's now gone. If it doesn't have a bomb, it's still now gone. You are alive. Of course, after 18 or 19,000 such flushes, there would be problems with the bathroom. That's a different story. But for now, you have succeeded. Do you understand what I'm saying? So you realize that even if, in fact, you may not actually observe. So this is the case. The bomb in the toilet problem is the case which corresponds to complete unobservability of the critical things. I mean, of course, you're seeing the toilet, et cetera, but I mean, the most important thing you're not able to observe at all. The most important thing is the bomb, you can't observe it. So if you can see, then it's fully observable. If you can't see at all, it is non-observable. If you can see partially, then that's partially observable. I mean, in this particular case, maybe, you shine a light on it without touching it. And then suppose you see some inside, shape, and that shape might give you a little more hint about whether it's likely to be a bomb or not. By the way, where do you think this actually is a real life issue? I mean, it's a real life issue, first of all, you realize this. All of medical diagnosis is based on this, right? Because you go with some random symptoms to your doctor, right? The simplest thing is take this tablet and call me tomorrow. That is, if you are dead, you won't call. So that's a completely fine thing, right? If you're not dead, you will call them. Do you see what I'm saying? So by the way, the plan for the bomb in the toilet, which doesn't involve B and T, no sensing. That means you never sensed whether or not there is a bomb and you are still able to survive. That is, basically, we should call it nonsense planning. There's nothing wrong in calling that, except in English, nonsense has other connotations. So we make a more fancy name called conformant planning. Okay, conformant planning, essentially, yes, you have a question? Or B and T, bomb in the toilet. BIT, whatever, bomb in the toilet. Right? Conformant planning. Basic conformant planning is going, in essence, one way of thinking about conformant planning. It turns out, let's see if I can get an empty slide. Oh no, there are no empty slides. I don't know why. Maybe there's one before. Yeah, so conformant planning. So conformant planning is actually going to start with a state which is more than one state. Initially, you can be in a state where there is a bomb, or you're in a state where there is no bomb. This is a belief state. You think you are in one of these states. Without resolving the uncertainty, you essentially say flush. And when you do that, you will be in a state, whatever the state is, you will be in a state, all the states that you are in at that point. Let's see if I can, yeah, all the states, yeah. So after you flush, you will still be not sure which state you are in. You probably are in some number of states. But in all those states, you will be safe. Do you understand what I just said? This is what conformant planning is. You're pushing all the sheep into, the pen in a sense. So all the states are being pushed into, as you keep doing actions, the belief state size might actually increase or reduce, or in general, in terms of distribution, the distribution might change as you do actions. And finally, when you're stopping, when in the case of these simple, non-deterministic states, you're stopping when all the belief states are guaranteed to satisfy, all the states in the belief state are guaranteed to satisfy the condition you care about. Be safe. Do you see what I'm saying? That's conformant planning. So compared to conformant planning, the normal planning just starts from a single state and tries to go to a single state. So when you do not have sensing ability, you are reduced to search in the space of sets of states. And that's much worse, because sets of states, given n states, there are 2 power n subsets of states. And that's why, life is much harder with conformant planning if you don't have sensing. And then, as I told you earlier, in the medical diagnosis kind of scenarios, the in-between thing happens where, in addition to flushing, you may very well have some other kind of an action. Let's say you can say B, not B, and then you say stethoscope. So you put the stethoscope on the bomb, on the package. And if you normally, as you know, have you seen enough cartoons, you know that if there's a bomb, it'll be saying tick, 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 right? And so if it's saying tick, 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 it's either a bomb or an alarm, right? One of which at any rate. Do you understand what I'm saying? If there is no tick, 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 there's no bomb. Do you understand what I'm saying? There, the stethoscope is a test. So doctors ask you to go for a random test. That's basically what is happening. When they do the test, the distribution changes. Distribution changes in terms of your belief as to what the underlying state is changes, because you have more knowledge. You see what I'm saying? The pure sensing action, so this kind of an action, stethoscope kind of an action, are called sensing actions. And these kinds of things are called causative actions. Okay, in general, that's actually a slight simplification. A causative action might also, the thing about sensing actions is they're in essence not changing the world, they're changing your mind. Do you understand what I'm saying? Suppose I asked, where is Obama right now? Right? And you come and tell me that, oh, Obama is in this particular address in Chicago. You could have done it in 2 different ways. One is, hey, Rao asks, my grade depends on it. I'm going to kidnap Obama, go put him in this address and say he's in this address. Then you have done a causative action. Do you understand what I'm saying? The other is you essentially called your friends in Chicago area and said, hey, is this guy still in his home? And if so, without disturbing him, you came and told me. Obama's place didn't change. Your belief as to where Obama is changed. That's what a sensing action does. Normally, medical tests are also supposed to do that. They're supposed to test whether you have the disease without causing yet another disease. But you all know that's not true, right? Because any interesting enough test, like for example, if you have a heart blockage, they will have to do, actually they have to send a probe into the heart to check if there's a blockage. In doing so, they might actually burst a vessel, in which case you'll be dead. That's normal. Okay, you basically have to then make a decision between whether or not you're going to take the risk. Or are you going to just say, to heck with it, I'm going to have an open heart surgery directly instead of checking whether I have a bad heart or not? The reason I'm saying this is real life. You do this. Sometimes tests, the sensing actions can have causative effects. And similarly, causative actions can have sensing effects, right? Because when you did put Obama in your kidnapping place, before that you couldn't know where he was going to be, but after you kidnapped, you knew exactly where he was. There is this old children's poem which says, this animal may or may not be sleeping, this animal may or may not be sleeping, and then finally the elephant then wakes up and yawns, and then now you know whether animals are sleeping or not, because all of them are awake. Right after that step, they definitely, whatever they were doing before, they're awake. It's the same idea. You're not, if I ask you, can you check if your friend is sleeping, not sleeping around, but just sleeping, right? You go and ask, hey, are you sleeping? That's not a sensing action. That's a kind of a nonsense action. You lose friendships, right? But you would know, but there is always, after you do that action, they would be awake and you get to come and say, no, he's awake, right? But think about this. This is real life. This is basically how sensing actions work. And you should ask, am I actually changing the fluent whose value I am trying to assess? And it's not a simple question. It's not a simple question, because instead of yelling, are you awake? You might basically say, oh, I know that if people are asleep, they might have their eyes closed like this. So I will use this black light on their face to see if they're asleep or not. Unfortunately, that too will wake them up. There's just so many things you can do that will actually affect the fluent that you are trying to assess. This is what the problem of testing actions is. But you do have to deal with the testing actions. And when you deal with the testing actions, then it's somewhere between conformant or nonsense planning and fully observable planning. Okay. But we're still going to stick with fully observable planning for now. And then discrete versus continuous, the number of states are discrete versus number of states, the actual state space is continuous. You know the difference between discrete versus continuous function. Okay. And then the other thing is static versus dynamic, which is, are there other agents in the environment? In the sense, if you actually looked at the state of the environment and you close your eyes and thought about what your next action is going to be, and it took about 5 minutes, by that time, will the environment still be in that state or not? If you are the only agent in the world, or if in fact the world is static, then when you are thinking, the world stops. Do you see what I'm saying? Whereas if it doesn't, then you have to actually do a much harder kind of a planning. In fact, this is why you don't actually go into the middle of the road and try to figure out, let me make the best plan. Because during that time, okay, I see that car is there, this car is there, let me make the best plan. Unless you take into account in your planning the fact that you only have these many seconds before those cars hit you, you could actually be hit. And so by the time you're ready to actually execute your amazingly great plan, you're dead, because world is dynamic. Okay, so that's the dynamic part. And so basically all of these are from Intro to AI. You should have known about this. If it's new, then this is the kind of thing that you're missing. By the way, the observability is an interesting thing. It is kind of an interesting combination of, is it a property of the environment or is it a property of your sensors? Do you see what I'm saying? So if you can't see it, is it because you have bad eyes? or nobody can see it. In fact, this is a hidden state of the environment, and you can't find that. And most agents would not know what the fluent is. Okay, so that is actually, you can sometimes separate that out and say imperfect sensor. So you can improve the observability. If you are in robotics, you can improve the observability by actually buying better and better sensors for the robots. In fact, for the longest time in robotics, basically people would be stuck with the robot trying to localize itself in an unknown environment. Many of you are in robotics and automation MS, right? Have you heard of SLAM? Simultaneous localization and mapping. That's what you're trying to do. You go into a new area where you don't know what the map of the area is, and you're trying to figure out where in that map you are. Do you see what I'm saying? That's very hard. And these days, it's not as bad because we have GPS, right? Irrespective, you may not know the map of the city, but you know exactly your longitude and latitude on the Earth because GPS is there. So people who still want to do SLAM sort of a thing will say in GPS denied environments. That means if you want to act, if you want to understand how people who can't see live in the world, you close your eyes, even though you have eyes. GPS denied environments can be there sometimes. And so actually, it's a much harder problem. But remember, the GPS has become possible because as a civilization, we essentially sent a bunch of satellites, they became geosynchronous, and then they're just giving us this information as to wherever you are. And in the old days, only a few people will have it. Now every random person has it. Like this morning, I was waiting for my case for my new phone, and I could see the Amazon tells me exactly where the guy is. So I could actually be seeing, and I was actually very annoyed that, before it said he actually dropped. So there was actually a lag, it turns out, of up to 3 to 5 milliseconds. So I was very annoyed that, it's not completely correct. But I was able to get this free. I mean, complete joblessness as on my part, but on the other hand, I was able to get this information free of some random guy holding my Amazon thing and going around the neighborhood. Oh, John is getting something too. Looks like he stopped at John's house, because this is all this stuff that I'm actually figuring out now. Okay, so in general, if you improve the sensors, you can make a hard problem easy. Okay. Anyway, so that's one of the things that you want to do. So that's about this. Are there any questions on this stuff? So ultimately, the easiest part is the orange part, deterministic. The other very important thing that I forgot to mention is instantaneous versus durative actions. And you may not have thought about it, but you live it, right? For example, you will say, I want to improve my your goal is, I want to improve my income, expected income. Then action, let's do bachelors. The damn bachelors takes like 4 years. In between, there are wars, there are Taylor Swift concerts, all sorts of other distractions, and this damn action is not getting over. It would be so much nicer, you say bachelors, and then the bachelors is over, and then you start making money. Right? In the real world, durative actions essentially means actions are concurrently going on. Multiple actions are concurrently going on. And the concurrency brings up huge, interesting questions. In general, when you talk about planning, when you talk about RL, etc., you forget all these other complications. We'll assume, in the case of normal planning, we'll assume deterministic actions. Non-durative, that means instantaneous. We'll assume discrete. We'll assume static. We will assume fully observable. And we'll assume goals of attainment. And once you have this picture, you can then see what are the starting assumptions for different areas that say they talk about planning. For example, control theory folks would pretty much never assume discrete. In general, the control theory started with continuous dynamics. So their default is start with continuous state spaces, continuous action spaces. Do you see what I'm saying? RL assumes full observability, and in the normal simple RL assumes finite states, discrete state spaces. Do you see what I'm saying? The problem is the same, but depending on the default from which you start from, it looks like a very different area. Once you figure that out, you can actually bring things across fields to bear. Okay. Okay, so that we did. So this basically, there are names for all this, once, okay, actually, yeah. So if I say static, deterministic, observable, instantaneous, propositional, that's called classical planning. Okay, that's the simplest planning, and we call it classical planning. That's what we will be discussing today, and a little bit of next time too. But if you understand that, then the problems there would become worse as you go higher up. And one of the things I tell my research students is, if you think that you have a great idea about the more complex scenario, ask yourself, what does that idea mean in the simple case, in the deterministic case? It is possible that the problem that you are solving doesn't even occur in the deterministic case. But more often than not, actually, it's not the case that, in fact, that problem won't occur in the deterministic case. And so you would actually see whether you are thinking your idea is complicated because of the environmental complexity, or is it really actually an interesting idea? Do you see what I'm saying? So you take the footprint of that idea on the deterministic classical planning. So it's a useful thing to understand classical planning that way. Okay. Then if I then start saying, if I remove the so metric temporal planning, what did we do it this way? Okay. So if I put durative actions, then it becomes temporal planning. If you put durative actions, it becomes temporal planning. If you put durative and continuous, it becomes metric temporal planning. If you put continuous only, then it is sort of numerical constraints, the sort of thing that control theory folks typically do, are essentially the sort of things that OR people, operations research people do. So there are different planning things, and the simple ideas for them might be very different for each of these special cases. Then if static versus dynamic, if you are in a dynamic scenario, one dumb idea is replan. If the world basically changed and you are not yet dead, then you say, oh, this is the state, let me go back and try to replan. Okay, and of course there could be better ideas than replanning. One idea is what I call situated plans, which is you compute what to do for every possible state you might find yourself in, such that finally you will get to your goal. Let's say Sky Harbor Airport. I want to go from here to Sky Harbor Airport. If things go normally, I can go out, I can ask a Uber or something, and that just drives on the road and then gets me to Sky Harbor. Suppose there is some kind of a bombing campaign going on and some additional, people, some sort of protest marches going on, etc., etc. Roads gets closed, Ubers stop, all sorts of random things happen. So now I'm in a different state now. Right? It happened to you, right? Once in a while, you'll go to the airport and find that all our planes have been grounded, or at least your plane has been grounded. And you don't change your goal. I mean, some of you might change your goal and say, oh, the heck, I never really wanted to go back to ASU anyway. I'll just hang around in Venice, which is a great goal. It's a newly arrived at goal, right? We actually get to do that, by the way. But if we don't have it and we still have to be at ASU, let's say, then you have to find an alternative plan, even though your flight got canceled. If after the flight got canceled, you figure out an alternate plan, that's replanning. If you're one of these, if on the other hand, you're one of these real paranoid people and say, let me figure out all the things that can go wrong, and for each of them, figure out how I would still manage to come back to ASU. That would be a universal plan. It's a policy which, irrespective of state you are in, it tells you the right action to do so that you will get to the goal that you're trying to reach. How many of you realize that, how many of you have heard of reinforcement learning? How many of you realize that what I just said is what reinforcement learning does? And do you or do you not realize that it's a highly inefficient thing to do if in fact the world is deterministic? Do you see what I'm saying? So don't always pat yourself on the back for doing the costly thing, right? You have to understand when to get by with a simple plan. Normal thing to do is, instead of getting a full universal plan, you should just basically get the plan that assumes the world behaves deterministically, let's say, and then start thinking, what are all the things for which I will make contingency plans? So there is universal policy. There is a line plan, and there is a contingency plan. Contingency plan is something that you have computed beforehand still, right? And the contingency plan says, under these conditions, if this happens, I will do the following thing. You have pre-computed it. If you haven't pre-computed it, you still have to replan. Yeah, I mean, that's basic, exactly. That's a very, very good question. I mean, yeah, thank you for saying that. I'm such a good contingency planner. My wife would love to hear this, but it is true, because I actually don't believe in audio video. In fact, it's the normal saying is that sometime after AGI, audio video systems will work as advertised. Until then, nothing is guaranteed. So normally, all these great AGI conferences and the audio video is where they get stuck. Okay, but anyway, so that's a contingency plan. We normally have a few things that definitely go bad, likely to go wrong. You'll keep an extra thing. But universal plan is considering all possible crazy contingencies. Replanning is, I'll just wait until the thing to go wrong and then I'll figure it out. The point, of course, is the replanning in a dynamic environment might be bad, because you may not have time to think. Do you see what I'm saying? The good thing about universal plan is everything has been computed beforehand. So all you need to do is, oh, this is the state, I'll do this action. Oh, this is the state, I'll do this action. And you computed all the policy beforehand. You overcomputed, basically. And then now, irrespective of what bad things happen, you will be able to look up the action. In the case of contingency plans, if you're good at figuring out what contingencies will happen, you will look them up. Right? If, on the other hand, you're not good at them, and then the contingency that happens hasn't really been planned for, you will have to plan. And one of the things you can do is, once you plan for that contingency, you might as well remember this. That's just memoization. So now you remember. So in fact, one way you can think of this is, let's see if I have I thought I put a whole bunch of white, oh, there's a white slide. Okay, good. I put a whole bunch of white slides just for this. So imagine this is S, and this is G, and this is a whole bunch of states. Right? As you know, a policy basically tells you what to do in every state. Oh, in this state, go this way. In this state, go this way. This is the picture that you all saw in the reinforcement learning. Right? Okay. A line plan, on the other hand, says basically just do this, 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 do this. That's a plan. That's a line plan. Okay? And you can go from this towards the fuller policy by saying, okay, I understand these are the states I'm going through, but maybe some of these states I might wind up, I'm sorry. In some of these states, I might actually wind up, let's say instead of being in this state, I might wind up getting into this state close by. So then I don't know what to do for that state right now. So I can compute what is the best way to get out of the state, get back onto the plan. In fact, how many times were you going on I-10 or something and they randomly close the rest of the thing. And they say, get out here. And then when you get out here, sometimes they put a detour so that they have already computed the contingency plan for you to get back onto I-10. Sometimes they don't, or you didn't see the detour sign. Then what are you going to do? You will try to get back onto I-10 if possible. Do you see what I'm saying? And so that basically is like saying, if I'm here, well, what I need to do is, oh God, don't do this, keep. Okay. All I need to do is, this is the action from that state. Do you see what happened here? If you think in terms of that being the goal, and that's just a random state, the right action is go right. But since you already have this plan, right, one idea would be to just go from wherever that other contingency back to your current plan. Do you see what I'm saying? So this, by the way, is, if you keep doing this for a whole bunch of states that might actually fall out of the expected path, you keep saying, how do I get back onto the path? Then in a weird way, you would be extending the envelope of the states over which you know what to do. This is actually a sane method for dealing with quasi-stochastic scenarios. Do you see what I'm saying? But what you would do in normal MDP and RL is you assume the worst case. Oh, there's stochasticity, so who knows what happens? In the end, you might as well just figure out the optimal policy which basically tells me the action for every state. Okay. Okay. So going back there, okay. So those are the names, some of the names. So this is the dynamic planning, that's the partial observable planning. And then if you have stochastic, if the deterministic then becomes stochastic planning. And if we're both, then it's partially observable stochastic scenarios. That's the one that you're talking about, POMDP sorts of things. So there are different subsets of assumptions you can. These are the assumptions for classical planning. If you keep changing some of the assumptions and relaxing some of the assumptions, you will wind up getting the other kinds of plans, other kinds of planning scenarios. So the point is, now we'll just figure out how to do this. This is the simplest case. But then it turns out, A, that it actually gives you lots of useful ideas about what to do for the other things. Okay, and B, if it matters, it turns out even this planning is hard. In particular, if those of you who are into ChatGPT can't solve these problems. Forget about the other ones. Okay. Anyway, so let's talk about how to do this. So modeling the deterministic planning problems, action states, and correctness. So the transition system perspective, first we just think in terms of individual states and an action as a state transformer. That's the lowest possible denominator. Okay. So Apple Pencil battery is low. What can I do? Okay. So the transition system essentially is a set of states and a set of actions, where A is a set of actions, and then each action basically is a sort of relation over states. If it's a deterministic action, it takes S1, I'll go to S5. S9, I'll go to S17, etc. So a way, if you think in terms of what would be a representation for this action, it'll be a matrix. Yeah, it'll be a matrix like this. Right? Because every action is an S by S matrix of zeros and ones, if it is deterministic, such that in no row is there a more than one. So all that is saying is that if I do action in this state, which state will I go to? That's where I'll put the 1. If I want to make this description into a stochastic action description, what do I need to do? Instead of ones, it will be just numbers between 0 and 1, such that the column adds up to 1. Okay, so there is really no difference. In fact, in reinforcement learning, when you tend to talk about actions, this is basically what is called the, if you actually have those probabilities, that would be called the transition function. Okay, but I'm arguing that actually this is like the simplest place where you're starting from. And so you can think in terms of these. In fact, this is basically what's called atomic representations. And atomic representations is where you try to understand things, but you never really want to do it at the atomic representation level in most cases, because it's just too inefficient. It's like you understand how to do differentiation as limit h tends to 0, fx plus h minus fx by h. But if you actually wind up doing derivatives in a calculus exam that way, you'll get a 0. Right? Because most of the time, you essentially will use faster heuristics that follow from these. You see what I'm saying? So something like that we'll wind up doing for the state spaces too. Okay, so it actually turns out that you can directly manipulate state transition systems. So for example, each action will be an S by S matrix. And if you want to compose 2 actions, you multiply the matrices. Nice. So you want to know, here is a state, and here is a state, and I have this action. What will the state be? I look up this matrix. If I want to do, what will happen if I do A1, A2, A3 from this state, then I can compute an A1, A2, A3 matrix, which is A1 times A2 times A3. And then I can look that up. Okay, so the things like that can be done in the atomic level, but atomic level is actually quite uninteresting for deterministic case. In the case of deterministic problems, let's see. So for the atomic case, deterministic planning is just pathfinding, So this is where, how many of you heard of A-star search? Okay, the rest of you have to figure that out. Okay, A-star search is the best way to, best principled way, at least one of the principled ways to search for the shortest paths in weighted graphs. Right? If I give you a weighted graph, where a weighted graph is edges have costs, and I give you a state, and I say find me a path between this state and this other state. That is the lowest cost. That's what A-star search does. Finding paths is basically what planning becomes in deterministic scenario. So for example, if I am in state S1, I need to figure out how to get to state S17. I can pick an action and see if it already will take me to S17. Most likely that won't be the case. Then I take that action, take some other action, multiply them, and see if the new action will take me to S17. If not, take another action, multiply this, and see if that takes me to S17. Do you see what I'm saying? That's basically what A-star search does. It essentially does the multiplication incrementally, right? So it says, if I'm in this state S, I can do action A1, I can come here, action A2, I can come here, action A3, I can come here, action A4, I can come here. These are the different vertices. From each of these vertices, I will consider other actions to see where else I can go, until I find an S17. Except, as you know, from Intro to AI, you don't just say, wow, I see an S17, I'm done. You actually have to wait until S17 comes to the top of the queue in the open list. And then when you pick it up for expansion, then you check, is this the goal I'm looking for? And if you stop then, and if the heuristic you used, and then if you basically use the heuristic h equal to 0, that means only use the g, then it will already be optimal. If you are using a heuristic, that means you not only know how far you have traveled, but you are also guessing how long you have to travel to get to the required state S17. Do you understand what I'm saying? So that heuristic will essentially give you cost to go. It's an estimate. And what do you know about that heuristic? It's an estimate. It can actually say h equal to infinity. That's the best way to get done very fast. Right? Basically, you give up. Okay. S7 to S17, infinite. Oh my God, who has the time for infinite amount of cost? Done, dead. So in fact, if you put h equal to infinity in all the states, that's the best heuristic for the lazy bums. You say, I couldn't do it, it's very hard. Okay. But of course, when you say that, if I then show you, it turns out there is actually a path, you didn't find it because you're a lazy bum, then you lose points. Do you understand what I'm saying? The other end is, you could say h equal to 0. Say everything is probably as close to S17 as everything else. In which case, you will do the maximum amount of search. That is called the uninformed search in Intro to AI. The question is, between 0 and infinity, you can put any other number. H of n is a cost estimate. The interesting thing, the beautiful theory of A-star search essentially says that as long as the cost estimate is less than the true cost, as long as the cost estimate is less than the true cost, which is H star, then you are, if you're using it, you're guaranteed to end with an optimal path. Do you understand what I'm saying? Because h equal to infinity, you would say, I'm done, and you are not done. Actually, there's a much cheaper path, and you didn't find it. H equal to 0, you will definitely find the optimal path. It's just, it'll be too costly. H equal to H star is like the best, but that requires you to not solve the original problem of going from S to G, but solve every problem of going optimally from every state to G, optimally. And if you do that, then you have actually computed the universal policy. Again, since a lot of you know reinforcement learning, what does H correspond to in reinforcement learning? What? Okay, let's see. H, this is the kind of thing that you will understand in this class. What does H correspond to in RL? Or actually, when I say RL, really it's MDP. Okay? Because RL is MDP, where the transition function is being learned on the fly. Okay, so what does H correspond to? So somebody said policy, right? Shall I write that? Who agrees with policy? People are using heuristics. If she was already right, Rao wouldn't have continued the conversation. That's not a good heuristic. But anyway, yeah. Who else? What is the answer? What? Expected reward? So okay, there's a very different things. So I will just say, first of all, you have saying something about expected, but you're also saying reward. You're also saying policy and the value. What? You meant value. Okay. Who else? No, the question is, which is closer to reward or value? because expected sum of rewards is value. Right? Okay, so it's not policy, first of all. Remember, it cannot be policy because policy, the range of a policy is a function. The domain of a policy is states. The range of a policy is actions. Do you understand what I'm saying? So that's why you write pi S A. So it cannot be policy. Okay. What about reward? R S to a real number. What about value? S to real number. But so the question is clearly heuristic is a number. So by the way, there is this idea called dimensionality analysis. You cannot, in physics, how many of you heard about dimensionality analysis? If I make a crazy equation and I say this equation is right because I had a dream, right? And you, instead of checking, you just basically check LMT are the basic units. You essentially use the LMT units to figure out what is the left-hand quantity and what is the right-hand quantity units in terms of LMT. And if they are not the same, it can't actually be an equation. Of course, you can always say, oh, there's a fudge factor constant that we call like gravitational constant or something that will require the rest of, will give you the rest of the magical limits, the dimensions. But so dimensionality analysis is very useful. So you know that heuristic cannot be policy. The question is it likely to be reward or value? I want all of us to get to the same page because I'll just assume that this is like built in for you. Otherwise, you will be lost. It's all just me talking and, you know, I sound good, but nothing is going through. So if it is a value function, smarty pants, what is then H corresponding to in the, so if in fact, H is the value function, is what you're saying, then what is the reward corresponding to? So remember, what I'm trying to do is the following thing. There are people, I mean, I'm trying to make connections between A star and MDP underneath it all. And there are people who know MDP, not A star. There are people who know A star, not MDP. There are people who just showed up because the cushy chairs are there and don't know either. For them, none of this is going to make any sense. You have to figure out what A star and MDP are. Okay, for those who understand A star and MDP, the question then is, you still tend to have understood them as two very different topics and you never put them together in your head. If there's one thing I will do for you, I'll force you to put every damn thing you know about this area together. That's the only way you learn new things, essentially. Otherwise, it's just compartmentalized. Oh, in reinforcement learning, this is true. In planning, this is not true. If you ever say that, hear yourself saying it after this course, hit yourself hard in the back and say, wake up. You know, they're basically the same problem. And so there has to be some actual more deeper reason. So the question then is, you know, it turns out that in A star, path becomes MDP policy, right? And in A star H, it seems people want to say is value or value approximation, right? So my question is, what is reward? There should be something on reward too, because A star is actually solving a special case of what you call reinforcement learning, which is deterministic known transition function. That's what it's solving. Yes, somebody was saying something. Yes. Yeah. The cost means, what is the cost in A-star terminology? What is the cost in A-star terminology? It's the edge cost, the C. Do you remember, A-star, we tend to talk in terms of G plus H. But what is G? G is C1 plus C2 plus C3 plus C4 until the last place you came to. Reward is essentially the edge cost. So one thing that you have to understand, again, if those of you who have taken 571 better remember this, A-star, in fact, you can think of decision making in two isomorphic ways. One is my goal is to improve my happiness. The other is my goal is to reduce my sadness. They're isomorphic. A-star tries to reduce your sadness. It tries to reduce its sadness. It tries to minimize cost. Normal RL formulation tend to talk in terms of increasing happiness, expected reward. It turns out actually that's not the only formulation. MDP has cost-oriented formulations. Control theory folks typically only look at the cost-oriented formulations. And so the control theoretic RL formulations basically will be much cleaner connections to A-star search, even syntactically. Because you won't use the word V for value, you use J for cost to go. And if I said J, you would have thought about cost to go must be obviously heuristic. Again, understand how people can be talking about the blind man and the elephant issue, okay? They can all be talking about the same elephant, but different parts of it, and they can vehemently disagree with each other. But the guy who is above them all can say, oh, this guy all basically talking about the same thing. And so in fact, we can arbitrage what is being said here into this, which is why I keep asking you, if you get a great idea for stochastic dynamics reinforcement learning, I want to know what does it mean in deterministic planning. Because there are actually connections. Okay. Okay, so deterministic planning is just A-star search, right? With heuristics. And the heuristics have to be admissible. Okay, one interesting question is we will actually spend some time talking about deterministic planning with the next representation, which is not states represented as these state transition functions, but you go next to essentially what you're discussing earlier. Okay, by the way, this is MDPs as general transition function. All of this has been said. I have a slide there, but you can think of MDPs essentially as general transition functions, which normal MDPs tend to think in terms of reward, but they can also think in terms of cost. Okay. And then the actions are general transition. Basically, they go from state to set of states. Okay, that's MDP. We'll get back to MDP much later. But I was already mentioning this because this is an advanced class and you should have heard about MDPs before coming to this class. And those of you who said, we did supervised learning, unsupervised learning, what more is there? Yeah, this is there. Right, that's kind of important to note. Okay, so the problem with atomic transition function is it's painfully inefficient. It's a good way to understand differentiation as fx plus h minus fx by h tends to 0, but we don't do it that way normally. So you tend to do what is called lifted representations. So what is a lifted representation? Lifted representation essentially involves explicating the structure of the states. The thing that we are not doing in normal state in the atomic representation is we are assuming states are indivisible. Like S1 is a black box. And then you do an action, it will take you to S17, which is another black box. It's sort of like social security number representation of people. Right? Each social security number corresponds to a single unique individual. Right? But if I give the social security number, in one weird way, I have given complete description of the person. But in many useful ways, I have given nothing about the person to you. Right? Again, unless you happen to have access to the social security number database and you figured out who the person is, and then you figured out, oh, okay, this is a man, has 2 hands and long hair and, whatever, dark eyes or whatever. So all these features about the person that you know now after converting. But before it was just social security number. So state representations in lifted representation is you can think of, those of you who come from machine learning, you say feature-based representation of states. Okay, but in general, you can say that if it's a discrete state representation, I have, if you have a discrete state representation, let's say I'll assume there are n fluents, we'll call it fluents, are state variables. So every state, so previously a state is a black box, but now a state actually is an assignment of values to state variables. And whenever you hear me say state variables, if you are coming from supervised learning place, just say features and you'd be happy. But essentially, that's what it is. The question, of course, is that the state variables essentially is the control theoretic and also more computer science terminology. Okay, a state is described in terms of state variables. So if I have n state variables, that means every state can be described in terms of evaluation of these values for the state variables. Okay, so one question, of course, is even if I get up to this, I can basically talk about, yeah, oh, that's not too good. That's not good. Yeah, so I can talk about state variables can be discrete. Can be continuous. Okay. In discrete, they can be Boolean. How many know what Boolean means? True, false, basically. They only have 2 values, Boolean. Are n-valued, multi-valued state variable. Okay. And more interestingly, even a subset of multi-valued state variable is cardinal versus categorical or ordinal. If the state variable has values 1, 2, 3, 4, 5, 6, 8, 9, 10, and these are cardinal, that means 7 is less than 10. 6 is less than 7. 5 is between 7 and 3. So there is actually an ordering of the state variables valuations. If they're categorical, then they're just like, the variable might basically say, the state variable basically is talking about the hair length, or hair color. Okay, and the hair color, I mean, unless you believe, like me, that gray is the best or something, right? There is no actual cardinality in the hair color. It can be a multi-valued thing. I mean, people can have blue hair, I mean, because they have all these bleaches, and they can be Smurfs too, and they can also have, yellow hair, they can have dark hair, they can have the gray hair. So this is a multi-valued state variable. But it's not cardinal. This is for discrete. Then when you come to continuous, you can also have a continuous state variables. And then again, In the case of continuous, typically we tend to think in terms of cardinal numeric values. Once again, to make life simple, we will consider Boolean. Why Boolean? Why? No, I understand, but why Boolean? What? I understand why. Where did the word Boolean come from? Where did the word Boolean come from? Ask yourself these questions sometimes. What? What does, what? Yeah, person what? What's his name? George Boole. What did George Boole do so that he gets to call? I mean, those of you who are smirking, you have no reason to smirk, my friends, because if you knew, you would have said why it's called why Boolean is interesting. What is George Boole famous for? What? Who said this? He's actually turning in his grave. Databases is so boring that George Boole would turn in his grave to think that all he did was databases. I mean, you can tell this to Selchuk, but when I'm not in town, but go ahead, yeah? What? What is Boole famous for? Who said this? What? Boolean logic. This is how far you are from logical reality because of all this, all AI is just supervised learning problem, right? And one of the things you're going to learn is civilization depended on us knowing logic. And in fact, logic is actually very important because logic provides the normative basis for reasoning. This is our best way of mathematizing what we call reasoning. Who actually said this first? Not Boole. Who said this first? The Greeks. Everything they said mostly, and the Greeks basically said that they started talking about logic is a way of understanding reasoning, understanding syllogisms, for example. How many of you have actually taken propositional logic or first order logic or some background in logic in Intro to AI? The rest of you are in big, deep soup. If you want to understand this class, you better go back and read at least my lectures, as impoverished as they are, in the Intro to AI and what logic is. I will assume you know, because I'm not going to teach you Intro to AI. You guys, those are the people who kept saying, there are bunches of people who said, I have done Intro to AI, it's about 60% the same as your Intro to AI. Oh my God, I mean, the important 60%, important 40% might actually be missing still. And so you better understand what logic is. Okay, please, really understand what logic is. Listen to at least my lectures. Otherwise, we don't have a common thing. We're just basically talking in generic vacuum, which is great because right now everybody else who is talking, for example, about LLMs can reason is in that same vacuum because they too have not understood what logic is, because most of them are grad students like you and they took neural networks, which is a great course, supervised learning, great course, and skipped logic. That's not good. Okay, so why Boolean variables? Propositional logic. All logic actually typically default thinks in terms of truth and falsity. So you think in terms of Boolean variables. That's the reason. I mean, that it took this long for us to understand why we are saying Boolean tells us how far we have, how basically far you went away from having any understanding about logical basis. Okay. Okay. So Now, if I have n Boolean variables, right? For just now, let's assume on A is a Boolean variable. And between us, it means A is on top of B. And it can be true or false. Clear B is another Boolean variable. I just made the variable names. Basically, just like in programming languages, do you have any restrictions on what you can call variables? Most reasonable ones, you can call any variable anything. Modulo special characters. If you are calling it with, in fact, the true programmers who don't want anybody else to understand their programs will call all of them I and J and K and I++ and JJK and blah, blah, blah. And so that it will be, how many of you heard of what obfuscated C competitions? Obfuscated C competitions are essentially, there will be this 1 or 2 line program, and that's written in such a way that it does something very interesting, but it takes you hours to figure out what the heck it is doing. Because they don't use the variable names that will give away any meaning to you. And it's actually very important to know that obfuscated C code exists, because otherwise juniors would be bozos and thinking that the computer understands the variable name. Computer doesn't understand the variable name, right? Computer just thinks of variable as a register. Right? The variable name is for you, the bozo who is looking at the program, who is not executing the program. It's the computer which is actually executing the program. Right? Okay, so I call these names just to make it easier for you. Clear B, it can be true or false, right? On A, B, clear B, and then holding A is another variable I made up that can also be true or false. That is holding a block. This is between us. Just how you write programs, right? You tell each other the stories that this variable is supposed to stand for this. Just because you told that story to yourself, the program isn't actually going to follow that, right? Because the program lives in its own reality. Okay? How many of you know that Shakespearean dictum that a rose by any other name smells just as sweet? That's what logic is. In logical theory, you can take all the names and change them consistently. It'll be the same logical theory. And if you think I'm talking nonsense, take a program that you just wrote, change all the variables names consistently. And the program, I guarantee you, will work exactly as before. Because the names meant something to you. It didn't mean anything to the program, the computer. And the same for logic. The meaning comes because of the connections between the variables. It doesn't come because of the name of the variable. This is extremely important because we are talking about logic, language, and meaning. And behind me, as like a big elephant called LLM standing, saying whether or not, if I call the right names, maybe I can do planning. Okay, anyway, so let me do this. We'll take a break. But so if I do these variables, I would argue that imagine you have a blocks world scenario where I just have 2 blocks, A, B, and a hand. Okay, how many variables can you have? I can have on AB is a variable. I can have on BA. I can have on AA, on BB, holding A, holding B, clear A, clear B, hand empty. And there's one more thing I can write called hand empty. That can be true or false. So hand empty. Can anybody think of any other names for just this little world? Only these names. They're all Boolean fluents. Right? How many Boolean fluents are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 Boolean fluents. How many possible Bloxworld states can you write? Because each of them should get a true-false valuation. So you start by acting as if state variables are independent. They're not, but you act as if they're independent. They're independent, you can give them independent valuations. So first one can be true or false, 2 possibilities. Second one can be true or false, 2 possibilities. So 2 times 2 times 2 times 2 times 2, 2 power 9. So I would argue that the state space here is only 2 power 9 for these Bloxworld domains. And then what would the actions look like? Actions would basically look like, I can write an action like this, that pick up A. Such an action, pick up A. Okay, and what it says is if you pick up A, the effect would be holding A. Effect would be holding A. And then, can you always pick up A? The precondition for pick up A is clear A. Because if A has something on top, you can't pick up A in this world. It's a simple way people play Bloxworld. It's not something that I'm making up. So now I actually start having these actions saying it has, if the precondition in the previous state has a certain valuation for certain variables, then the new state will give certain new values to some subset of variables. And the rest of the variables just come off from the previous state to the current state. These are called strips actions because this is the representation that was generated by strips planner, the Stanford Research Institute planner back in '72 when they had the world's first robot doing block stacking called Shaky. I'll show you the picture of a Shaky and in fact the picture of Shaky with me in a minute, okay? But that's what they came up with. This is a representation. Okay, so we will take 15-minute break. Keep thinking about this. You come back, I'll talk about using this representation to do planning. And also understand what are the requirements that you want to introduce on this representation. Okay? Oh, okay. Okay, are we all back? more or less, hopefully. Okay, so this is just a different way of representing the world, where basically you can think of it, as I said, as a feature-based representation. Okay, where of course there are interesting questions that come up whenever you start talking about features, which is when I give the social security number of a person, I have abstractly captured pretty much everything about them, even though you have no idea what I captured. But if on the other hand, I said, I'm going to represent the person in terms of their hair color and whether they have eyeglasses and how tall they are, etc., there is always some aspect of them that I did not capture. And so you can always say the representation is not complete. Do you understand what I'm saying? It's not that the other one is complete. It's just I made it by definition complete by saying it's just a black box. And so whatever you say, oh, it's there in the black box. It's what I'm saying. So in fact, one of the interesting questions, and this is actually a pretty serious question, and you have to think about this. You have to think about this, that is completeness of state representation. Okay. Atomic states are vacuously complete because they don't say what they're actually modeling. Okay. Whereas any state variable representation or a feature-based representation will be of necessity possibly incomplete. One interesting question is the way you can capture that incompleteness is you can say there are hidden state variables. What? What? Atomic states are vacuously complete. Yeah. Right. So the point is that any specific any feature-based representation, think about it in the same way. Feature-based representations can always be incomplete because you didn't capture all possible features. And given any task, maybe there's a particular feature that you did not even know existed. In fact, civilization went around. One of the things that you have to say is that we never actually, even though we talk about black box state representations to make thinking easy, civilizationally, we never thought about black box state representations. We always described things. Do you see what I'm saying? And we have sometimes forgotten what are the important variables, and we had to figure out much later that there are other variables of importance that may not even be sensed. In the past, for example, we'll assume that the color of the skin is an extremely good indication of a whole bunch of things about a person. And there's no reason to kind of act as if, oh, who are these people? They are our bozo ancestors who did actually believe this. And civilizationally, we figured out more knowledge, and we figured out that there are hidden variables. And in fact, the things like color of the skin are these unnecessary, irrelevant variables for certain kinds of aspects of, what happens, in terms of what happens in the future of a person. So in some sense, to even say something is irrelevant, you need to think of what is relevant. Do you understand what I'm saying? It's easy to kind of, if you don't have the relevant variables at all at hand, you're going to scapegoat some variable into saying, yeah, that must be the reason the bad things are happening. Remember the poor black cats, civilizationally kind of hugely stereotyped? I don't like cats myself, but on the other hand, come on. I mean, it's like a black cat comes, if you're going somewhere, you die. Right? Right? Despite the fact that you had taken a couple of swigs of whiskey and you were driving, you say it's really obviously the black cat. Right? Because the other features are actually more relevant, but why care about that? Because so the point, of course, is that things like, and again, if you think about what happens, again, by the way, medicine is full of this. How many of you read, if you haven't, you should, The Emperor of Maladies? It is a book. Anybody read? Anybody read? Anybody does anything outside of the classes in general, other than eating pizza or something? So, Emperor of Maladies is by Siddhartha Chatterjee, which is actually a biography of cancer. And it's extremely useful to read it to understand how primitive medicine is, even yesterday. And so tomorrow, today's medicine will be primitive. Why? Because our knowledge is constantly evolving. I mean, remember, the old medicine was, if there is a headache, then you make small holes in the head so that the pressure is I mean, this is what we were doing, and you laugh at it, and you read Emperor of Maladies, you would hear about these nonsensical things like radical mastectomy for curing, quote unquote, breast cancer. There was no connection, no real causal connection, and then basically people will come up with newer and newer papers. Medicine is a completely observational science. There's very little causation goes on oftentimes. And so in fact, if you notice, statistics departments flourished in medical schools because biostatistics is a thing. You actually don't know how anything works. You just say, we gave this guy this, this medicine, this other guy this medicine, fewer of these guys died, so this must be a good medicine. Let alone the fact that those guys were drinking Coke all the time, and that's why they became obese and they died, and it has nothing to do with your medicine, is going to be ignored. Right? So in general, one of the things that happens, actually, I would ask you to read this because correlation versus causation. Causation is like the most hard-won knowledge of civilization. What causes what? Correlation is probably the poor man's civilization, poor woman's civilization, lazy people's civilization, right? And the more you actually figure out what causes what, the more knowledge you have about how the world actually works. And it's not obvious, because to understand the causes, you need to sometimes actually start modeling the hidden variables. So all of this is to just basically say that, vacuously speaking, saying S1 looks like a complete description of a state called S1. Whereas if you say the feature descriptions, you'll say, oh, no, you forgot this other part. You forgot the fact that A is a block that is colored red with yellow stripes on it. Do you understand what I'm saying? I didn't model it. Right? In general, you model whatever features you feel like, and then you basically start reasoning with respect to that. Okay, so it's worth remembering that it's not that the other one is actually taking care of things. It is that modeling any real world system completely is impossible. Okay, and the other interesting question is, when I came here, pick up A, and I said preconditions clear A, effect holding A. The idea in writing this is that I want to define transition. I want to define action transition this way. If I give you a state S1 and I do pick up A on it, I should be able to construct the representation of the state that follows. Do you understand what I'm saying? That's the basic idea in writing this actions this way, because any action needs to tell you what will happen if you do that action in a state. In the atomic cases, it told you, because if you do it in S1, you will get to S17. That's the black box representation. Here, both S1 and S17 are actually feature-based states. So when I say whatever is the new state, I need to actually give the state variable representation of the new states. So imagine the following situation. Imagine the following situation where you had B here, A here, hand is empty. That's the state, initial state. So you can write down the variables, right? For example, you can say on AB, and you can say clear A. On AB, clear A. You can also say hand empty, and more other things. Okay. Now, when I write pickup A, remember that if you remember what I wrote, pickup A, I wrote it as pickup A, precondition clear A, effect holding A. Right? Effect holding A. So the question then is, so effect is holding A. So the question then is, what is the state here? You know that in this state, holding A would be true. It wasn't true before, but holding A is true now. What? Oh, okay. So I have to write the hand empty. So that's right. So hand empty. And it is indeed the case that hand is empty, right? Okay, that was fine. Holding A. What else? What? Clear B. That's a weird thing to have to write. Right? You understand? But if you didn't put, why did clear B become true? Clear B definitely wasn't true before. It has to become true afterwards. So I better write it here, clear B. Because otherwise, how am I going to figure this out? There are two ways of figuring it out. One is I write whatever definitely holds, holding A, and then I use the logical theory of states in Bloch's world. And in the Bloch's world, if there is nobody on top of you, you are clear. That would be essentially theorem proving. And if you know anything about logic, propositional theorem proving is NP hard. First order theorem proving is semi-decidable. Okay? So what you do instead is you put the onus, typically this idea of making sure that all the variables it changes, all the state variables whose values it changes must be represented in the effects. Do you understand what I'm saying? That is called the strips assumption. So basically, the strips assumption is actions must specify every fluent which will change its value from the preceding state to the next state. So for each action, there's a preceding state, the state that comes after that action. The action should basically completely describe all the things that it changed. And once it says that, everything else can be written over from the previous state. Right? Because those are the ones that are not changed at all. Do you see what I'm saying? One other minor thing that people tend to do in this kind of representation is, if you are in a fully observable world, which is what classical planning is, so you know the complete initial state. Right? If you know the complete initial state, you can just write the variables that are true and ignore everything else, because whatever is not named in the state must be false. Do you understand what I just said? This is only true if the state is completely described. If, on the other hand, the world is not observable, you don't get to make this assumption, because maybe it's actually not, you didn't even observe it, And that's why you don't know what its value is. If you have observed every state variable's value, then you get to take a shortcut and just write the ones that are true. Okay. Typically, sometimes people tend to do that in this kind of a scenarios, and that's what's called the CWA, or closed world assumption. It's a particular kind of a closed world assumption. I've looked at all the state variables, and so I know their actual state. So I just have to write I pick whichever. If I like truth, I just write the true ones, and then everything else that's not listed must be false. If not, then actually a more reasonable thing to do. In fact, this strips assumption is an important assumption. Without doing strips assumption, you would actually have to do theorem proving in the next state to figure out what the true state is. Do you understand what I'm saying? So actually, I'll write that down here, that without strip, oh my God, where the heck am I going to write? Yeah. Without strips assumption, you will need to do theorem proving in the next state. It's not the end of the world, but it's a pretty costly thing. Because then the state will be incomplete, and then you will have to say that anything that logically follows from what is given is also known. By the way, that actually brings me to another very interesting point, and I wish, okay, I'll use this. Okay. Imagine you have a state where you wrote on A, B, and didn't say anything about clear B. Actually, given on A, B, you know that not clear B must be true. Because in Bloch's world, the general background axiom basically is for all xy, on xy implies not clear y. I'm assuming you know how to write logical statements, right? This is a background axiom. And if you have this axiom, and then you apply, you give the on A, B, then it follows not clear B. What follows doesn't have to be said, because it doesn't actually increase your knowledge. And that is what has been called deductive closure. If I give you a bunch of facts like this and that, then I run theorem proving, it will figure out all the other things that will just follow from it. That's deductive closure. Okay, if basically stuff that is following by logic, you didn't realize it, that's because you're just lazy. Do you understand what I'm saying? So the distinction I'm saying is that in this world, if I were to tell you, hey, did you know that not clear B? Versus, hey, did you know on B, D? Those are two different kinds of knowledge. The first knowledge you have, you just didn't realize. The second knowledge, I don't know where the heck D was until I told you there was no D for you. And I'm just saying B is on top of D. It's like that whole turtles theory. I mean, there's a block under the block under the block under the block. And I just told you which block is under B. That's new knowledge. Philosophically, these are two very different kinds of knowledges. One is deductive, one is inductive. Do you understand what I'm saying? So normally you say you actually increase your knowledge mostly for the second case. The first case is you made implicit knowledge explicit. Right? If you know the rules of chess, the game of chess is trivial. You understand that, right? Because how do two infinitely omniscient robots play chess? Have you thought about it? I mean, you bozos play chess, waste a lot of time. I don't play because I'm bad at it, so I decide it's a bad game, right? So you bozos basically, oh my God, what do I do? How do two infinitely omniscient robots play chess? The first guy thinks for a second, makes a move. The second guy thinks for a second and says, I lose. Why? Because with respect to that move, they're actually able to see the entire infinitely large chess tree. How many of you know min-max backup? And min-max backup with a limited depth is what bozos do, like us, are people with computational things. If Jensen Huang has to have his way, and I hope he has his way because I own a couple of shares of NVIDIA, right? The way it is going to be is that everybody should be able to do full-on theorem proving. So you should be able to go indefinite depth chess tree and then back it all up. And then you might realize that it's definitely a dead thing. And the rest of us are thinking, how did this second supposedly infinitely omniscient robot give up? Well, that robot knows something that you are blinded to, not because inductive knowledge, but because ability to complete the deduction. Do you see what I'm saying? Sometimes you might, I mean, like if, for example, if I say, oh, I'm trying to figure out what is 4 times 3, 4 times 3, and I'll tell you it's 12, unless you've been dropped recently on head and you forgot everything that you learned, I didn't tell you anything new. If I told you it is 17, at least something new. Right? At least then there's something new that is not following from what you know. Okay, so it's very, very, very important to understand the distinction between deductive closure, and that's basically knowledge that's already present in the implicitly present if you just do the logical inference. But the problem with the logical inference is computationally very, 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 very expensive. For propositional logic, it's NP hard. For first order logic, it's semi-decidable. For anything above, it's basically undecidable. Okay, so, but still there's a difference. One is computational ignorance. The other is actually true ignorance. That means you don't actually know the value of this thing. Okay, so what the strips assumption is doing, strips assumption saves you the trouble of computing deductive closure. You understand what I just said? That's all it's doing. Because you don't want to be actually in the exam, let's say, sometimes people want in exam like logarithm tables. Why the heck do they want logarithm tables? Because they're like lazy bums, right? I mean, calculators. Because everything is known. Once you know the numbers and multiplication, etc., everything is known. But then, it's because the exam is time constrained and you don't want to spend your time doing multi-digit multiplication. You want some either calculator or some, in the old days, in my time, we would be given logarithm sheets. How many of you even know how to use logarithms to do multiplication? I've actually done it? Wow, that's very good. You must have used punch cards too then. Okay, great. Okay, so we should talk. I think we are basically at the same age, at least computers wise, honestly. But, so the interesting thing basically is that we save the time of computation by giving those values. Okay, that's what is basically, strips assumption is doing. Okay. So this is block's world description. It's one block's world description. Okay, so essentially, I'm just saying, these are the variables. Maybe I may have missed a couple of descriptions, but I think this mostly the actions are correct. It has like 4 actions: pick up, stack, put down, unstack. And you can essentially see that I have made sure to write. Okay, I can't remove this for some reason. Yeah, I've made sure to write, for example, on stack xy, I'm saying it has to have on xy true, and hand empty must be true, x should be clear, and then fx should be holding x, not clear x. Notice that if you are holding x, x is not clear, can be just an axiom, but you have to write it anyway, so that you don't have to do deductive closure. Okay, and clear y and not hand empty. These are the actions. And so similarly, you have put down action, a pick up action, a stack action. This particular representation, this action representation, this is basically preconditions and effects. It's a pretty standard representation written in logical format with predicate names and variable names and etc. The logic syntax, right? There is a language that is called PDL, Planning Domain Description Language. It's just a specific syntactic way of specifying actions. And if you look at the syntax of the actions in this, it looks very natural to somebody like me who thinks Lisp is the world's best language, and very ugly to the rest of you heretics who think Lisp is a bad language. Okay, so basically it's in Lisp syntax. Okay, and then so it's like a define, and the problem is defined in terms of the domain and the objects, the initial state, and the goal specification. And the domain itself is defined in terms of the actions and their descriptions. Right? So for example, here is an action, move. It has the parameters x and y. Its precondition is and room x and room y, and at Robbie x, that robot Robbie is in x, and effect is at Robbie y and not at Robbie x. And notice that this second part is strips assumption. Right? You had to say, even though instead you could have just said a simple axiom saying nothing can be in 2 places at once. And from that, it follows that if the Robbie is at y, then it definitely is not at x. But that would require actual theorem proving. And if you don't want to do it, you do strips assumption, where you actually say everything that actually will change. Okay? That's the homework for next week. So we'll give you basically a homework to write for some simple domains that we will describe in English. You will write PDDL descriptions in terms of preconditions and effects. And then the question, of course, is, did I model it correctly? For any model of the world, you have to ask yourself, have you modeled it correctly? Well, it turns out that we will provide you essentially a simulator, where you will execute this plan, and it will tell you what the state is. And if the state is the goal state, you'll get points. If not, you won't. Do you understand? Fair enough? This is basically what should be actually. So it's not a pretty hard thing. It's just to get you to use this, So I think there are like a couple of funny domains that they describe in English. And then you just have to write it, and you have to, the question then would be what predicates, etc. I think they actually tell you which predicates to use, because if they have a simulator, they have to tell you which predicates to use. Okay. So that's going to be the first homework. Now, the jumping ahead, like jumping way ahead from this was 1972 strips planner used this representation. The syntax for PDDL actually came much later, but they used a different, I mean, just before, like, PDL is like the Python of this little subfield. So it sort of became the way to write the action representation. But before that, everybody will have a slightly different way of writing, and that's what they will use. Strips has its own way originally. But interestingly, when you actually are doing this homework, you have to ask yourself, how did I figure out what are the preconditions and effects of these actions? In essence, I made you the expert for this domain by kind of describing the domain in English. And then you act like an expert and you start writing the model. So you are what has been called a knowledge engineer. You took knowledge in English, wrote it in PDL so that a planner can use it. By the way, that's what you are anyway, right? You take some specification of somebody's problem in English and write a piece of Python code. And when you do that, you say, we are software engineers. So since this looks like logic, we'll call you knowledge engineers. It's the same. Right? You are the middleman, the middle women, and that's what you get big bucks for. Okay. Brokers always make more money. This is a sad world. But anyway, so that's the question then is, can we cut the middleman out? Right? What is that crazy company that is trying to cut all your jobs so that there'll be more and more students in my classes? The company that is Devon or something, which basically says LLMs can be used to generate code. And what? Devin. See, yeah, Devin, the company, which is a bogus company, it turns out, because on the day they put the advertisement saying we have automated software engineer. On the other side, they say we are looking for 100,000 software engineers jobs. Why do they need it if they have automated it? Right? You know that they obviously are making something up. But anyway, so the point is Devin automates software engineering with LLMs. Here is Rao trying to tell you knowledge engineering. Why can't I have LLMs automates knowledge engineering? At the level at which Devin automates software engineering, you really can automate knowledge engineering too, for pretty much the same reasons. So if you don't believe me, there is a paper that Lin Guan had in NeurIPS from my group. I'll send you the link, which essentially that paper is about how to use LLMs to tease out actions and the preconditions and effects for a given model, for a given domain. Okay, and of course, one of the things that you will see, I mean, I'll repeat it multiple times later on, that nothing about LLMs has any guarantees about correctness. LLMs is like anti-computer science. It doesn't believe in any kind of guarantees and correctness. If anybody says LLM is guaranteed to do anything, stop them right after guaranteed. Okay, all it is guaranteed is to give more tokens. That's the only thing it is guaranteed. That the tokens have any property, no guarantees, none. Okay, if you can find something that they actually do with guarantee, be my guest and tell me. Okay, but essentially they give great guesses. Guarantee essentially means it's always correct. A good guess means it's most of the time correct. LLMs are good idea generators. And they have been trained on the entire internet of data. Everything that we ever said. So like when I started talking about blocks world, you weren't very surprised when I said pick up, put down, stack, unstack. Right? Because you are competing in your own head. Yeah, that sort of makes sense. I mean, I did play with blocks when I was a kid, and true, I didn't have a fancy robot hand, but I had my hand, and maybe this is what he's talking about. And the reason you made sense of blocks world is because you have played with Bloxworld. Do you see what I'm saying? And LLMs have played with everything you have not played with. LLMs have footprints of everything you ever played with. There is nothing on the internet. I mean, it's like the talk about privacy, right? Pretty much everything that we ever did, we wound up writing it on the web. There's a bunch of things that we did, but there's a lot and lot of stuff that we put on the web for our crazy consumption. And then LLMs came and just took it over. And my usual thing is, imagine if Sam Altman got all the gazillions from Satya Nadella for getting the GPUs, but just didn't have the web. Or the web was there, but nobody put any data on the web. So then he says, hey guys, do the needful, as we would say in India, and just put stuff on the web. It won't happen. In fact, anytime they had to put stuff on the web that is not already existing on the web, they had to pay people in Nigeria big bucks. One of the probably the only good things of one of the big good things about OpenAI is that it improved the GNP of Nigeria. Because people, they would be actually getting some of this knowledge that if you put it yourself, you don't expect people to pay for it. If I ask you to put it, you definitely expect. So you guys might be tweeting. You guys might be writing random text messages. But if all I need to say is, every day thou shalt put 7 text messages, then you'll say, what's in it for me? What's the salary for these 7 text messages? Why am I going to do it free for you? Do you see what I'm saying? Okay, so without caring about any payment, we put all of this stuff and no more is going to be put necessarily. And so we have to understand what is there, and we have to understand the fact that much of this stuff essentially captures a whole bunch of things that you didn't even know exist. None of us really understand what is on the web. None of us even understand what is on Wikipedia. Forget about web. Wikipedia is the clean part of web. Right? I mean, again, remember there was this time when people were talking about what is a Palm, which is the ancestor of Gemini, was able to explain jokes. And that was seen as AGI because, LLMs are just trained to be the next token predictors. And yet they were able to explain jokes. Must be AGI. But how many of you are humor challenged like me and realize that there are places, like every once in a while, right? When people are talking, they'll tell a joke, everybody laughs. We also laugh because even though we don't understand the joke. And then we had to ask like sheepishly, hey, why are people laughing? What is funny about it? In the old days, that's what we have to do. Now we take our cell phone, write the joke out and say, internet, there is a web, there is a repository which explains jokes. I'm not making this up. People do crazy things free. Right? And so because of that, that data exists, so it is able to use it. Similarly, it has data about Bloxworld, it has data about rockets, it has data about weddings, it has data about travel, it has data about everything. So you can ask what are the preconditions and effects for what are the actions, what are the preconditions, what are the effects, you'll have a reasonable guess. Woe be unto you if you just take the model that it gives as the first step and say, oh, definitely it's working. Okay, but on the other hand, you basically put it in like a more reasonable, like a workflow where you take the guesses from what the LLM is doing and do some syntax checks and do some minimal intervention from the human knowledge engineer. Then you can reduce the time humans would spend in writing the models. Do you understand what I'm saying? So that's basically, as you are doing it next week yourself, you can see that there could be, if you are into it, a way of doing it partially automated with LLMs. In fact, minimally, you can just ask, hey, this Bloxworld in particular, that's why we don't ask you Bloxworld. Bloxworld, you can just ask in ChatGPT, what's the Bloxworld domain model? And it's been trained on enough Bloxworld domain models, you'll just spit one out. Right? I mean, that's pretty much the reason why Copilot works. Right? Pretty much there is a bunch of pieces of code that you have to write repeatedly in new contexts. In the old days, I used to think that even as I speak, some bozo is writing an exponential time algorithm for topological sort being well paid in Intel. Now, I still feel unhappy that they're being well paid in Intel or whatever, but at least they can just go to Stack Exchange and get the, the correct topological sort. And Stack Exchange is also full of bozos who will freely help other people. I have this problem. Oh, okay, fine, we'll stop doing what we're doing and we'll help you. This is the crazy thing about humans. We just do random help to people. I know I'm kind of a misanthrope in that sense. But the point is that if you are actually writing that sort of a code, most of the GitHub code essentially that you put is pretty good quality code. And for standard tasks, essentially Copilot will guess pretty reasonable pieces of code. If you don't check for its correctness, you will pay for it. And in fact, the way they will do in software engineering, which is not this paper, is they would let the Copilot. I mean, there are two ways. One is if you are a human in the loop, you will let Copilot guess a code, and then you look at the code and say, hey, it looks good. I'll take the chance of me losing my job. Or it looks good, but this small minor change, I'll make that change and then I'll use it. There's nothing wrong with that. That's human in the loop. If you don't want to have the human in the loop, then you need to have an automated workflow, which basically one way would be that you might have some unit tests. You'll say for this problem, if you give this input, this is supposed to be the output. If you give this input, this is supposed to be the output. And one of the nicest things is there exist Python interpreters. You might be thinking I'm saying something strange, right? Because in a world where LLMs are supposed to do everything for you, they didn't do Python interpreters, thank goodness. Okay, Python interpreters have this beautiful probable property that if you give any piece of any string, any long string that corresponds to a Python syntax, more or less, at least, they will at least try to interpret it as a Python syntax and then tell you for an input what would be the output, right? So if you have unit tests tells you for this input, this is supposed to be the output. This input, this is supposed to be the output. Here is my program that goes into the Python interpreter with this input, gives this new output. You compare it to the expected output. If it is wrong, then you know the code is wrong. If it is right, the code can still be wrong. It's just right on the current unit test. This is same way of using code generation with LLMs. And that's actually how it's being used right now, if you look at research papers. And if you think about what's going on here, that's sort of what approximately happens. You can read the paper and it'll become more clear after a couple more classes. But basically, he will let PDL domain description be kind of guessed, and the planners interpret PDL domain descriptions. Planners, which are the things that we're going to discuss in a minute. They are the Python interpreters of the PDL world. Okay, and then you can use that for unit testing. Plus, of course, the humans can still be in the loop and then provide extra information, etc. So that's one way that LLMs can come in. So there's actually more information about LLMs for constructing world models. And the last thing that I want to say before I go into a couple of slides about actually planning procedures is this is the homework today, right? The homework for this week is writing the domain models. I'm just saying you can use LLMs, right? The next homework would be actually making plans. That's what I'll tell you, how to make plans using forward search, backward search, plan space planning. That's what I'll tell you. And I'll tell you very quickly today and then come back again next class. But you might be asking yourself, if it's blocks world, why can't LLMs just generate the plans? Why take this class? In fact, why take any class, honestly? First you should just give the class name to LLM and say, what should I do? And it'll just basically tell you, right? Something. So a reasonable thing is this is actually one of the things that our group does. And So this is basically all the state-of-the-art LLMs currently, if you can look at it. Except Claude, the most recent Claude, everything is there. GPT-5 isn't there. And if you ask them why is there no GPT-5, they have actually got some shrills who are saying, oh, they're going to skip over GPT-5 and go to GPT Nirvana, which is like the real final GPT. But anyway, that's a very different story. But so, and you notice blocks world, this little block stacking problems. We made 500 blocks world problems, randomly generated blocks world problems, which all of them can be solved by the 1972 Strips planner with 100% accuracy. And pretty much everything that you will learn in this class will also be solving them with 100% accuracy. So we let LLM, generate the plan, guess a plan, guess it with maybe COT, guess it with some multi-shot versus single shot. Again, for those of you who know, but we'll talk a little bit later. And then we actually check what percentage of the plans are actually correct. Okay, and so you'll see that it's not that high. We are supposed to depend on these things for AGI, right? So even in blocks world, it's not 100%. And these are like 12-step plans maximum. Even more interestingly, forget about blocks world. There is this other thing I wrote called mystery blocks world. It is mystery blocks world. It's for the end of the class. Okay, but the interesting thing you notice is mystery blocks world, they're all 0. Forget about 50, it's a 0% accuracy. What happened? How did Rao make this up, or how did Rao students make this up? It turns out that it actually came from planning community, the stuff that you're taking the class on. There's this guy called Drew McDermott, who 1998 basically had to set up the international planning competition, where people will come up with planners, and they're supposed to be domain-independent planners. Now you know what domain-independent means. They should be taking the domain description and the problem description and generate a plan. And then they'll check whether the plan is correct or not. And they'll also check how long you took to generate the plan. And then Drew basically was worried that maybe, even though we are requiring people to do domain-independent planning, people might be doing domain-specific planning. That is, techniques that only make sense for a particular domain. If you don't believe that, you understand the following thing, that in blocks world, irrespective, what will the input look like? There will be an arbitrary configuration in the initial state. You want to put it in another arbitrary configuration, the goal state in the blocks world. If you don't mind writing just a piece of C code, forget about all this state representation, progression, regression, large space search, all this nonsense. If you want to just write a piece of C code, you can do the following thing. Take all the blocks, put it on the table. Then put them in the right order. The length of that plan, first of all, that plan works. And secondly, the length of that plan would not be more than 2 times the optimal length of the plan. Do you understand what I'm saying? Imagine the scenario where I have A2 to A100 as one stack, and A1 is sitting on the table, and I want A1 to A100. The optimal plan is 1 step, just basically 2 steps. Pick up A1 and put it on A2. But my approach will actually undo the entire block stack and then reconstruct it. It'll be 100. Or more than 100, no, 400. So in general, you can see that what I'm saying in this simple approach will give you plans that are within twice the optimal plan length. And it's a domain-specific idea. It only makes sense for blocks world and nowhere else. And what if people were doing that kind of a cheating? So he was worried about that. So then what he decided was basically what we were discussing in this entire class, which is the names of the variables are for the people, not for the interpreter. Right? Just as Python interpreter doesn't care whether you called a variable student's height or SH. The plan interpreter also doesn't care whether you called a predicate on AB or like some other crazy thing, eats AB. Do you understand what I'm saying? It's just a string. So what he did was he took something like blocks world, pick up block, unstack a block, put down a block, etc., and obfuscated the names. So this is obfuscated C for you. And you, as we know, obfuscated C program runs just as efficiently as the non-obfuscated C program. It only makes you go crazy. Right? Because you have no clue what the heck it's supposed to be doing. But give it to the computer, it knows. Right? Who is the computer here? LLM for us. So what he was doing in his case was he was doing this so that if they have written a piece of code which will say, if there is things like on and clear, then case 1, which is for blocks world. And if it has something like truck, etc., it's case 2, that's for logistics. And you won't know that they're doing this. And so you can be basically, they're doing domain specific and they're winning the competition. This is what he was worried about. But now LLM comes to game. Right? So the question is, if LLM actually was solving these blocks world problems, can it solve these equivalent blocks world problems? They are basically blocks world in different names. Do you understand what I just said? Think of a Python program, change variable names consistently, that will still be equivalent Python program. Does anybody disagree with me on this? I'm not questioning that the second one would be so much harder for people to understand. Right? But the question is, can you do planning? Can you actually run the code? Okay. So if you do this, basically, this is what he was doing it for that. And if you do this kind of a obfuscation, then pretty much all of them just die. The question is, if I give these obfuscated versions to Strips Planner from 1972, would it die? No. Would it do faster? Would it do slower? No. Would it do faster? No. It doesn't care. Do you understand what I'm saying? It's the same reason. If you take a Python program and change the variable names to be crazy variable names, the program's efficiency doesn't change. If you take a Python program that has bad variable names and you improve the variable names by putting ugly underscores in between, do you think the speed will improve? Do you think that program will start working better? No. It's just that the Bozo TA will give you more marks saying readable program. Who asked them to read it? Just give it to the computer to begin with. It's meant for the computer anyway. I mean, I'm being facetious. I understand programs are actually, as Kanut says, programs are written for each other. It's only as a side effect, they are supposed to be run by the computer. Okay, but the fact remains that if in fact you can actually make it, if somebody is making a claim saying I can do planning, they should not fall from whatever is bad, which is 57% to 0%. This is June. Do you understand what I'm saying? So you don't need to worry that when we come back and talk about simple ideas like, I'll tell you this, simple ideas like progression, which is start from the state, apply actions to generate new states. You know how to do this, and then do a star search on them. Or regression, which is start from the goal state, apply the action in the reverse way, which is a critical, more funny thing that we'll need to think a little bit more carefully about. We'll do it next time. You should also read about this first. Okay? Then you can do search this way with a star search. Okay? And if you don't like either of these, you can also do plan space search, where you essentially put the actions into the plan and start putting ordering constraints between them. and keep introducing new actions anywhere in between. Remember, I told you this last time? The way we generate plans is not starting from the initial state going forward or starting from the goal state coming backward. We put in the important actions and start putting the other actions as they are needed in the right places until the plan becomes correct. That's plan space planning. So you can do search in plan space planning. Let's see if there is this for that. Yeah, so yeah, plan space planning looks like this. I'll walk you through this next time. Okay, so essentially it searches with a partial plan, which is a set of constraints, and keeps adding more constraints. The constraints can be adding actions, adding ordering lists, constraints between actions, etc., until finally the partially ordered plan is guaranteed correct. And you're done. And I'm going to drag you through these. And you might be worried, why am I going to be dragged through this if LLMs can already solve it? I just told you they don't. So at least just like, like your software engineering job might be somewhat, basically your plan knowledge engineering job and your plan writing job might be, it's there until GPT Nirvana comes along, which whatever the heck that is. Okay. We'll stop here. Thank you. And have a nice Labor Day.
Could you go back to the plan bench slide?
Plan bench slide? No, I didn't have the plan bench slide here. Do I?
No, like you're showing the results for like.
Oh, this one. Yeah. Yeah. Benchmark slide. Yeah.
Yeah. So I noticed that.
Yeah, I know what you're going to ask, but I'll let you ask and I'll tell you.
Okay. Like for
okay.
some like models, like zero shot performance extraction pattern.
That's exactly what everybody asks.
Okay. So
And basically everything you heard about LLMs is bogus. Unfortunately true. Okay. You assume that the more shots will actually make LLM do better. But one of the interesting things is actually when you give the example that can actually push the LLM in the wrong direction. By its own background knowledge, it might have been slightly better off guessing a better plans. So there was no actual guarantee ever that K-shot reasoning does better. In fact, our entire work is mostly debunking most of these ideas. That K-shot stuff doesn't make sense. Chain of thought doesn't make sense. Self-verification doesn't make sense. So at least you'll hear the other side of the story. Okay, and that's why we are putting it right there. It turns out that if in fact it's a universal, so your worry is it must be a universal law. And since Rav's results don't agree with them, Rav must have done the wrong experiment. That's a reasonable question, right? But if you do the experiment, you'll get the exact same answer. And then you will start realizing, oh, actually K-shot doesn't necessarily improve performance. Actually, chain of thought doesn't necessarily improve performance. Much of what happened is people pick and choose the results they report, unfortunately. And we are all in this nice hype cycle. And so we are more likely to believe positive results. Believe positive results. Like 1 second, I need to do something.
Yeah, I think that explains. Any other questions?
Okay. Yeah. Yeah, that's the point. Yeah. Yeah.
Okay. Yeah.
Okay.
It's my first class of this subject, and I didn't attend the first class. So regarding assignments and the quizzes, everything, I don't have any audio on this.
I think whatever I said in the class is what is there. I mean, the 2 lectures are there, and basically, as I said, there would be projects and there will be actual term projects, and there may be exams. That's it. And this is a research class. This is not meant for ensuring that there'll be 8 small texts and tests, and there'll be etc. Yeah. Again, I went through all of that. So there are 2 different kinds of projects. One type of project we will allow group, and another type of project, which is basically survey project, you won't allow group. You should listen to the entire lecture that you missed. The audio at least is completely available. You can just listen to it and you'll get all that information. Okay. So that at least you'll be in the same place. I won't be telling you something different. Yeah.
For the assignment, it's like when is the first, like when will we be getting the first?
When everybody gets it. not separately for you. Whenever everything happens on Piazza, there would be an announcement when the assignment is released. And then you will know, just like everybody else at the same time. Okay? Just 1 second, let me. What do I do? Okay. Yeah.
So I know the midterm or final, like the exam schedule is currently undefined. We don't know yet if when.
I don't even, yeah, basically, no. I think that there is a final exam date that they provide for this class, that if we have a final exam, that would be the day on which it will be held. Midterm, I will let you know if we are having it, when I'm having it. I mean, everybody gets the same. I know. I think every class is the same. Midterm basically is somewhat in the middle of the semester, but.
That makes sense. I wanted to ask about a specific day with me traveling to check out like grad schools. And I was wondering like if there's.
I mean, I think basically, if my point is the contingency of that cannot be done,
Yeah.
if you wind up having a conflict, if there is, like what I'm saying is, I would say, wait until that conflict arises and let me know. I mean, it won't be that I would tell you that day that's the exam, right? So I will let you know that there's an exam, and if you find that there's going to be a conflict, let me know and your reason and first thing, and then we'll get it.
Okay, great. Thank you.